All right, so okay, let's get started. Welcome to our fourth episode of OpenCV Weekly Webinar. And today we are going to have a very interesting episode. We have Brandon Miner with us, who is the CEO of Tangram Vision. And as always, Phil Nelson is there to help us with, with the questions, etc. And the reason this webinar is very interesting is because we are going to talk about a variety of sensors, and it's going to be fascinating. But before we do that, let me introduce Brandon Miner. Brandon, would you like to introduce yourself?
Yeah, sure. So hi, everyone. My name is Brandon Miner. I'm the CEO of Tangram Vision. We're making DevOps for perception. So Tangram creates the layers that stitch your sensors together. The topic of today's conversation is how those sensors, will work as a unit. And that's really what we do, right? We make your platform work the way you want it to, so that the data you get is perfect for your application. So welcome. Thank you.
That's great. And like we said, this episode is a lot about different kinds of sensors, not color cameras, right? So the right way to think about it is that what is the information we can use in different kinds of computer vision applications, which are beyond just the color vision cameras that we use. Now, Brandon can start, you can start by showing the slides, and then we'll go from there.
Sure. Okay. Let me share my screen here.
Yeah, the tagline for this episode should be "Let there be light." The entire
Man, where was that yesterday, Satya?
I know.
Yeah.
How's it looking? You got it?
Oh, that's great. That's great.
Perfect.
That's great.
So yeah, let's roll with it. So sensors for your sensors. This will make more sense as we go into it, I promise. But let's get started. Basically, why do we have so many sensors on these types of platforms is my question to you. So, let's take this AV, this autonomous vehicle, but we can easily substitute it with any mobile robotics platform, even an industrial arm. These sensor modalities are everywhere. We have cameras on the sides and the front to get visual light. We have radar and LiDAR to see distances. We have ultrasound, which uses sound clicks in the same way as LiDAR and radar to pick up, short distances at a rapid pace. But, the bigger question emerges, these all do things, but why are they all there, right? And the answer is really, we need more out of them. There's these platforms have become so sophisticated that the more sensors you have, the better. However, the underlying question to that question, the underlying need there is that these sensors each have deficits that other sensors can fulfill. And we're going to dig into that during this talk.
So the diagram you're showing, it shows what is the range of things, right? The purple, it shows what is the range of radar and LiDAR. The blue one shows, it's a broader area that it covers. The cameras, they have a bigger field of view. And similarly, ultrasound has, it's for nearby objects, I'm guessing, right?
That's right.
So, yeah. So ultrasound works the same way as, it's reflecting sound, etc. And we are going to talk about radar and LiDAR in the next few slides. But let's start with, grayscale and color cameras.
Yeah, the original topic of today's talk. So like Dia said, let's start here. Visible light. We're going to go through the optical spectrum as a whole today. It's going to be really fun. But let's start with what we personally can see, visible radiation. That leads us, as we said, to grayscale and color. Grayscale cameras are really easy to use, right? They take the entire color spectrum and smash it into the pixels, gives us a grayscale image. You can see on the left here, this is an image I took at the Denver Museum of Art. It's supposed to be wonderful and pretty, but all you get is, these alpha values. And that's fine. We're capturing a whole part of the spectrum. This is efficient information gain. It's what you want. But if you wanted more information, and as computer vision scientists, we always think more is always better, you're going to slap what was called a Bayer pattern on top of that pixel array. So you can see that here. The Bayer pattern is BGGR. blue, green, green, red filters repeated over the entire pixel array. And what that does is filters out those specific wavelengths of light into those pixel wells. So over the B, all you'd get is a blue. Over G, all you'd get is green.
So Brandon, I mean, correct me if I'm wrong. These are literally filters. These are thin films, physical filters that allow you, that allows only blue light, green light, and red light to pass. And it's actually located over 4 pixels, right? So,
That's right.
So you have the pixel array. If you're taking a grayscale image, each pixel, each element of that pixel array gives you 1 pixel. But if you're using a Bayer pattern, this Bayer pattern is spread over 4 pixels, as you can see. And a single pixel is recording only either green, blue, or red part of the spectrum. And can you explain a little bit why we use the two green channels and only 1 blue and red?
Yeah, so that purely mimics the human eye. So the eye has more green receptors, it's more sensitive to green. And so to do the same in our images, biologically inspired, we put 2 greens in there. That's the specific Bayer pattern. You can add other dyes there. There are plenty of other ways to do this. I kind of expound upon some in my blog post because you don't always want to mimic the human eye, right? If red is important to you on the road, say, you would just add a red filter and be done with it. That's all you needed. But for photorealistic images that kind of mimic what we would see, BGGR is most commonly used. It's an industry standard. And most importantly, it's produced en masse. So you'll see it everywhere. Yeah.
So it is the cost also that comes into play, right? It's that this Bayer pattern is very easy to produce because it's produced for everybody. So you might as well get one for your camera. Now, one thing that I had always wondered about, when I was in school, why can't we have are there other kinds of patterns like, instead of BGGR, are there other patterns? And you just mentioned there are. Can you name a few, which are less commonly used, but maybe in some industries, they are much, much more common?
Yeah, so, I already mentioned car cameras. There are a few with, instead of BGGR, you would have 1 red and the rest totally clear, like in a grayscale image. So you get most of the information from the visible spectrum, and then you focus a little bit on the red.
But why the red for the car?
Because warning signs on the road are red. That's it.
Okay. That's and even yellow, it's on the red side. It's a warmer tone compared to, it's not. Yeah.
And you'll get some of that information filtered out.
Okay, I learned something new too.
Yeah, and it also interesting. You can also use filters or dyes. I think I could be wrong here, but BGGR I think is a filter, but you can also have cyan, yellow, and magenta, like what you would see in the printer, as a dye on top of your photo array, and it gives the same effect. Instead of being, additive, it's negative light, flipped like that. And so, you get a ton of different color combinations, even on the materials scale, which is super cool.
Right.
Yeah.
So if you have a very specialized computer vision application, you don't necessarily need to stick to the color camera. There may be special filters or special cameras that are more appropriate for your application domain.
That's right.
Yeah. Okay.
But for our purposes right now, Bayer's fine.
Yes.
We can do a process called debaying to obviously grab the colors that were supposed to be there. There are tons of ways to do this. In my blog post, I put the most naive way, which still kind of gives an okay model, but it wouldn't be, something you'd want to write home about. And you derive the color. You derive the color camera. You now have more information than you originally did with grayscale. And one would think, given more is always better, that this would help your computer vision pipeline.
So one thing, the audience may not know, Brandon is referring to a blog post, and this is a blog post that was published on opencv.org recently. So you can go and check out that post also. It gives much more detail about these Bayer patterns and other kinds of patterns.
I'll go ahead and drop the link in chat right now.
That would be great. Thanks.
That's a good point. I did not assume anybody read this blog post, but it is explained there. Thank you. So yeah, we get new information, we get more information, but we find that if we're actually putting this into computer vision stand, we don't get more out of it. More information isn't necessarily better here. And it's because of that debayering process. So by the very nature of a Bayer filter, you're actually getting rid of the information not part of the filter. So you're getting rid of the red and the green if you're filtering out blue. What this means is that you've lowered your signal to noise ratio to a point where trying to clobber it back together introduces artifacts that you might not have even thought about. And here are some of them that are most commonly found. So chromatic aberration, you can see on the edges of this building, the debayering thought it could find some color, but it really failed. And so everything comes out blurry on the edges. That's no good. Moire effects is when you have intense grid-like patterns or repeating patterns, and interpolating between those pixels actually just gives you even more of a pattern. And so it looks like there are waves coming out. And this is something you see a lot when you take a picture of a computer screen, for instance. It's rows of pixels, and interpolating pixels over pixels, you're going to get some, grid-like effects. False coloration is one of my favorites. It's when your debayering is trying too hard. So on the side of this silo, there's blue and yellow, but the only things blue and yellow in this image are the sky and the ground. So what the debayering probably did was say, these images or these areas look like other parts of the image. I'm going to get colors from those. And in reality, it just failed horribly. Right. And then this last one, jagged artifacts, this is a direct relation to the lowering of signal to noise. Like, you just got rid of information. We don't know what's there. We're going to zigzag our way through it. So.
Yeah, so one other thing I want to mention is that when you take a picture in RAW format using, an SLR camera, it's always in, some sort of a Bayer pattern. You can get the raw Bayer pattern out. And if you actually want to understand what algorithm is being used, because it's not simple interpolation doesn't produce very good results. So there's a lot of things that goes once you get the information out of the camera sensor. You do Bayer interpolation, and you also do tone mapping so that the colors look right. They look like human eye instead of what the camera measures. It's a linear image. If you look at the linear image that comes out of a raw, out of a camera, it's very dark. It's not pleasant to look at. So there's a lot of processing that happens when you go from the Bayer, what information the camera records and what's finally produced so that it's visually pleasing. It's a whole process, right? And when I was in grad school, there was this tool called DC Raw. I don't know whether it's still used or, if you want to look at the code on how this thing is done, I think it was called DC Raw. You could check out DC Raw also.
Wow. And this is a great point. And something I avoided in my blog post specifically, because there are so many ways to do this, and so many color spaces that finding this finding that is impossible. So please look those up. It's super cool, but definitely not something we can dive into today. Yeah.
Right.
So we found out, more information isn't always better, because in reality, we didn't get more information. What we did was an interpolation of the information we did have. But this doesn't mean that color is useless, right? Grayscale, for sure, gives you faster data, and it gives you more accurate or a higher signal to noise, right? And so if you want fast processing of geometry, grayscale is perfect. If you need more semantics and a richer understanding of the environment, and you're willing to risk these artifacts or willing to go through the processing to make these artifacts go away, color is perfect. But in both cases, and this is important because this is the frame of the rest of the talk, you need visible light. If you don't have visible light, if it's dark, if there's fog, if there's clouds, et cetera, it's not going to work. And so where do we go from here? How do we compensate for these sensors? The answer is just to go to the other part of the spectrum, right? And so we'll start going through UV, IR. We'll find out how all these things stitch together. And Satya, Phil, stop when, or please feel free to jump in as we go through.
Yeah, so I mean, I have just one, comment about UV imaging. Usually, I have this little story that my wife actually got a UV light and to check a few things, and I was not sure what this is for. So if you take a UV light and look at, shine it in your bathroom floor, you may be surprised. So I will just leave it. I would just leave it at that. Especially if you have small kids, you will definitely be surprised. So shine UV light.
All right.
Shine UV light on your bathroom floor, and Okay,
Open for a surprise.
Yeah. Yeah, that is an exercise to the reader. UV imaging in robotics could probably have the same application, but here, it has a couple of niche properties that we want to explore, right? So UV imaging, we're shifting down. We're actually shortening our wavelength to get out of the visible spectrum. We're still in the optical spectrum. That's UV, visible, IR, but we're on the lower end. So, most UV imaging works with UVA. I think sunscreen is blocks for UVA through C. So there's a bigger range there. But it works best in sunlight, right? The sun gives out UV rays, works best in sunlight, unless you have a UV source, in which case you can do the same thing, but most people don't, just sitting offhand. And it has some really cool properties. Like, for instance, when you take a picture of the horizon in UV, you don't see clouds because clouds don't protect against the sun's UV rays, which is why you should wear sunscreen. But here in this picture, you can see the skyline perfectly. You can imagine that if you had a car wanting to, if you had a robot looking at the horizon, using that as a point of reference, the constancy assumptions that are inherent in all computer vision applications can be much easier to enforce when you don't have clouds moving in your image throughout. So this is a really cool little niche application of UV light, but it's a niche application, right? It's a very narrow band of info. It doesn't work without sunlight. And the information you get is only as useful as, a grayscale image with some things thrown out, right? You're just shifting down the spectrum. So again, we need more. We're going to need more out of our system. This may not be the most we can get.
But that's a fascinating thing. You have written in your slide that wear sunscreen even when there are clouds, because UV passes right through clouds. That's very educational, which also means that you won't see clouds when you're looking at the sky, right? That's exactly fascinating.
Yeah, please wear sunscreen. So yeah, UV gets us some things, but it doesn't get us all. So where we go from here, go to the other side of the optical spectrum, IR. And this is something that's much more common in computer vision sensors. For instance, into RealSense, occipital structure sensor, even some passive sensors are IR, but they're narrow. These IR imaging that we're talking about here are huge. They take the entire IR spectrum from 1,000 to 14,000 nanometers. So really long waves. And what it basically interpolates is thermal heat. So you can imagine, again, the sun shooting down. You can get a very clear picture of the heat signatures, the IR coming off of this tree via the spectrum. But again, it has its drawbacks. It may seem like a very big spectrum, but it's really only giving you certain information, just the thermal signature. And it won't work without other IR. So anything that absorbs IR, like really shiny black objects or that reflect IR, you won't be able to see. So
So one thing, Brandon, it would be nice if you could explain some of the applications. You had mentioned that UV is used for
yeah.
detecting plant disease and other things also.
Yeah, of course. So
Yeah.
yeah, there are some, even though they are niche, there are some really cool applications being worked on for UV and IR. UV specifically, though you can pass through clouds, very cool. You can also use this for biological processes, as Satya kind of alluded to. For instance, there are some labs, companies I know that are using UV and supplemented with other information visible in IR to better understand the behavior of plant health. So you can actually predict plant health 2 weeks in advance based on the imaging patterns you get off of the UV, visible, and IR combinations, which is really cool if you're trying to do indoor farming, for instance, where you control all of the parameters and you want to know how those parameters have tweaked the behavior of the plant. You can actually check this, monitor it scientifically in real time with these imaging techniques, which is very cool.
That's great. And now, the IR has several applications also. For example, the most common application people think about is night vision, right? That you can enable night vision when you're looking at the scene with IR sensors or IR cameras. And at the same time, there is thermal, which is slightly different from night vision. In a lot of night vision systems, you could actually be projecting light onto the, IR light onto the subject or the scene. But in thermal, you don't have that luxury. It's basically looking at a different spectrum and so you need different sensors, and they are way more expensive than regular IR cameras.
Mm-hmm.
Right. So Brandon, do you have an idea about, what is the price difference? A thermal camera, again, it used to be very expensive, $10,000 or $20,000. I don't know whether the prices have come down now.
I was looking at this yesterday, in fact, and I kept hitting marketing walls, I guess. It'd be like, contact us for the price. And I'm
okay.
One of those, if you have to ask, you can't afford it.
Yeah, I was like, I'm not going to do that because I think I'm not quite your clientele. So it is a mystery to me, but I guarantee you, if you have to contact them for the price, it's probably something niche.
One of the early applications that IR was used in, or at least I saw it, was eye tracking, and it is still being used. So in a lot of head-mounted displays, you have you have an IR light source and an IR camera, and it's used for eye tracking. So basically, this IR source of light is throwing light at you, and you cannot see that light because it's IR. But the pupils dilate, and it works the same way as red eye filters, red eye concept works, right? In older cameras, when you took a picture, the flashlight was co-located with the lens, right? Almost very close to the lens. And when you took a picture, you would see these red eyes. These days also you can see those red eyes, but people automatically remove them, cameras automatically remove them, so you don't see them as much. But it used to be a big problem back in the day. And the same technology, the fact that the eyes would dilate and would reflect light is used for pupil tracking. So, you turn something which was a disadvantage and a nuisance into something which is an advantage. And it's used even now in a lot of eye tracking, systems where they want to see, where is the user looking at, or even in head-mounted displays. That's a very common, eye tracking system based on IR.
And we'll actually get into eye safety in a few frames, because that is a good point. You can't just shoot IR, from 1,000 to 14,000 into your eye. You won't be happy about it. But there are ways we go around it, and we'll touch that in a bit. So we have now hit the entire optical spectrum. The question is, where do we go from here? Because it seems like we've compensated for all the things we can in the optical realm. We can get here, we can get here, we can get here. We can use what's called, I touched this before, hyperspectral photography to do all at once. Sometimes that's super cool technology, not quite off the shelf, but when you can use it, it's very cool. So what do we do from here? Well, basically what, computer vision scientists have done is added the other dimension, right? We're on 2D, let's go to 3D. Let's see how much 3D real-time information we can get. And the spectrum work we've done here, we can build on there. Firstly, through active depth. So, I come from an active depth background. I used to work at Occipital, which, developed the structure sensor and structure core, both of which had an IR emitter that shot IR out into the scene, kind of what Satya was referring before, and you could pick up that IR and understand the environment through it. And that's called active depth because you're actually shooting out IR instead of receiving the IR that's in the scene. And that works at a certain spectrum, 900 to 950 nanometers, maybe a little bit more to 980. But you want to keep it there so that, when it shoots into your eye, you're not sending too much information or sending too much energy, right? It's eye safe lasers. The advantage to these is that you get really good fidelity depth at ranges pretty close to you, from 0.5 to 5 meters. You get really clear depth, which you can see with me lounging in my chair here, getting shot by IR rays. It's very cool to see in action. It almost feels like magic because it happens nearly in real time, right? But the drawbacks are that because you have these restrictions on the IR band that you're using and the energy that you can pull out, you have bad performance in things that interfere with the IR. So sunlight, if you're using active depth in the sun will eat your IR rays. There's nothing about it. So you can't work around that. And it's also short range because there's only so much power you can send to that laser to get it out. So even if you're, mathematically, the farther your lenses are apart, triangulation is more accurate at farther distances. The closer they are, you get less accurate distance. I didn't do that very well with my hands, but it's true. Yeah, but it's basically short range, right? There's only so much you can pick up.
Shout out to any current or former occipitalians in the chat there. I'd just like to remind you all that swords are dangerous.
Yeah, and use this hand motion as much as you can when describing what we do.
So this active depth, Kinect sensor also used it, but is the industry moving towards time of flight sensors from these they're almost like projector camera systems, right? You project light onto the scene and then you detect them, and then you have a projector and the camera instead of two cameras. They're using the same concept, but instead of using two cameras, you're using a projector which projects a pattern onto the scene, and then you're looking at it through a camera. And since you know what pattern is being projected, you can triangulate, you can detect and triangulate.
That's right.
So that was the standard technique for these sensors. Is the industry now moving to time of flight sensors from this?
Well, I mean, I have in my hand a L515 from Intel. I can tell you it works pretty damn well. That the depth I get, well, it works, but the depth I get is beautiful. Right. And that couldn't always be said for things like the Kinect. For instance, there was a lot of calibration you had to do, even on an academic level, to get that working the way you wanted. So I think it is probably moving towards time of flight, and I think for good reason. It's just simpler mechanically, and it gives just as good results. So yeah, that's a good point. But again, it's still the same. You're shooting things out, measuring the impulse.
In fact, if you look at not necessarily commercial stuff, but if you want to get back in the day when if you wanted to get very high resolution scans, active depth was the only way to do it. And in those cases, they used to project these very thin patterns. So, when you're trying to get very high resolution reconstruction of a static object, you don't need it to be real time. In that case, you can project these patterns at very, a fine level and detect them, and you can get a very high quality reconstruction of the object you're like a vase or something that you're trying to reconstruct. So those used to be very popular for high quality reconstruction, and maybe even now they are.
Yeah, but again, you hit the same problems that you did with an IR sensor. If your IR gets absorbed or reflected,
yeah,
you've lost that part, and sometimes that just can't be helped.
Yeah.
So we'll touch on this later because there are ways to get around that, but they can also be compensated for by just raw power, which we'll see on our next modality. So like we said, active depth, you can get a pretty good idea for a short distance. It's a very granular resolution, which is very cool. You can get very big images with beautiful depth profiles. But what about long distances? Like, what if I want to see 50, 100 meters ahead of me? This will not do. So what we do instead is do the same thing with a lot more power, basically. So we give it LiDAR, which stands for light detection and ranging. And it's light detection because we're still in this optical band, right? As you can see on the right, we're either in the near IR spectrum, so still shooting out those IR rays, or visible green. Visible green is probably, if you're familiar with LiDAR, and I have one here. Here's the Velodyne VLP16. It uses near IR, and it does a pretty good job, right? It shoots at 16 bands. You get pretty good fidelity. But if you're in a scene that you think will absorb IR, you can actually switch to green, and it will work the same way as a green screen, in that the green that it shoots out is very rarely seen in nature. And so you can actually just reflect it right back to you and, have a pretty consistent measurement profile from that color. So it's very cool. It's just shooting really bright green light. So it's eye safe as well, to my knowledge. Don't look into a green LiDAR. I did not,
So I have a question for you on LiDAR, and I have not read enough about this myself. Our team, OpenCV.ai, they have deep expertise in LiDAR, a lot of work they have done related to LiDAR, but I personally have not, right? So my knowledge is pretty limited on this. Now, the question that I have always had in mind, and I'm going to ask it, is, when you have a single autonomous vehicle with LiDAR, and it's shooting all these rays and capturing it back, then that's easy, right? We know the math and everything. What happens if every vehicle is
shooting out
yes,
these rays?
Yes. Does it interfere, or is something else used?
Yeah.
It is like active lighting, right? It is active lighting. So you have to reconstruct it properly. It's not like passive, like a RGB camera.
That's
where,
right.
there is no interference. Everybody can look at the same scene without any problem. But does this cause any kind of interference?
My guess. So this is a good question, and I don't, despite having worked, tangentially on autonomous vehicles, I do not know the answer. My educated guess would be, so LiDAR is active. It shoots out very focused, very powerful beams of light. And so what that would probably do is allow you to measure it even through interference, I would think. They're very powerful light. It's pretty strong, very focused. And so I would guess you could go a long way just picking up the same signal, doing something smart about that. But if you had 4 or 5 in a room, I'll have to play around with that. I've never had 4 or 5 LiDARs to play around with.
Yeah, I'm just thinking of a situation where everybody is driving an autonomous vehicle. Does LiDAR become they start interfering?
Is there a saturation point at which case they stop working?
Yeah, that's a fascinating question. And if anybody has an answer in the chat, please
chime in.
Please chime in. But what I can tell you is that a single LiDAR does have points of failure. for instance, because of this focused beam of light, the shorter wavelength, you actually can read finer, smaller objects.
Mhm.
But what this means is that the finer, smaller objects might be water particles in the air, right?
Oh,
It could be
wow.
fog, it could be
Right.
rain.
Right.
And so if you're working outside, you could actually be getting the signature of rain in your LiDAR, which you don't want. It's not going to be helpful, right? So this interference of bad weather is actually something that, autonomous cars, for instance, have to contend with, as well as anything outside working with a LiDAR.
In fact, that's the exact problem we worked on recently at OpenCV.ai.
Oh yeah,
Yeah.
that's cool. How did you get around it?
I don't know the details, frankly. I mean, that I was not heading that project,
Mhm.
but they were dealing with exactly the problem of removing fog or the effects of fog in their LiDAR measurement.
Mm-hmm. Yeah, it's an open question as far as I know. It's just a thing sensors do. So you have to worry about it.
So one other thing that comes into picture often is, when you have transparent or even reflective surfaces, stereo vision falls apart because stereo vision is based on this assumption that if you're looking at something, then it looks the same from two different locations, right? There is but that assumption doesn't hold when you are looking at something which is reflective. You turn your head, let's say a piece of metal. If you take a piece of cement or something, you look at it from any angle, it's going to look the same.
Yeah.
But if you have a piece of metal, then it's reflecting the surrounding. So obviously metals, etc., they do not do well when you're trying to do this. When you're trying to do this, right? Stereo vision. Do LiDARs, etc., also have similar problems?
I
I
don't
know
know.
glass, it definitely gets confused with glass.
I'm sure it does. It's the same light properties, and there's no reason why it wouldn't, I think.
Right.
Yeah, LiDAR. It's the same as light. I'm sorry.
Yeah, that's
that
right.
sucks. Yeah.
That's right. In
Yeah.
fact, the new
okay.
phones. The other thing that I was fascinated about LiDARs is how much the price has come down.
Mhm.
And now your phone has a LiDAR, which is, it's sometimes I feel that I'm living in the future.
I believe some of our old coworkers worked on that, in fact.
Yeah, it's nuts how much that cost has gone down, but it's still not accessible to everyone, which I think is the interesting part. It's just getting to that threshold where you can get the hardware. You may not know how to use it, right? But you can get it, which is super cool. But that brings me to my next point for LiDAR. This next point of failure that I think is often surprising is that the long distance of LiDAR makes some people think that it is a cure-all as far as depth goes. But actually, it has restrictions as well that are very important, especially in these autonomous vehicle contexts. And I'll illustrate that thusly in this blurry graphic. So, if you have a heavy car, say semi, it's going 65 miles an hour, which is a very reasonable pace, American pace, to go for a semi. It takes 525 feet, or about, I think it's 150 something meters to stop. However, the LiDAR max range for most even common LiDAR or uncommon LiDAR, very powerful LiDAR, is less. You can get about 490 feet or something at the most powerful. And even then there's some uncertainty in your measurements. So what you find is that if you're relying on a LiDAR module to tell you when to stop for a heavy truck, you're going to run into something. And even this is something that I think is overlooked for car companies that are smashing LiDAR on top of their cars left and right. This oversaturation problem, if you will, is that it doesn't always work. If you're speeding along at 90 miles an hour, you're going to have to take some time to stop, and you might not know what's in front of you when you do. So again, how do we compensate for this? How do we see farther? How do we see in the rain? How do we get around LiDAR restrictions? And the answer to that lies outside of the optical spectrum. We have to abandon IR, UV, and go straight to radar and new frontiers, if you will. So we're back to our car. We've kind of done a full sweep of the sensors, and we know exactly where we need to, compensate for here. We can't see long range. What do? Radar. Radar works rain or shine because the waves are so long, they have very little interference. They don't get reflected back unless it's an object with some heft. And even then, what you find is that even though you can see much farther now, 5 meters too long way, radar and sonar both, this is what you use for weather images, right? It's huge. You can do a lot of distance, but it has much lower accuracy than LiDAR because of its physical properties. It's a much longer wavelength. It can't hit the fidelity that LiDAR can as far as points. So what you see in radar is basically heading of an object. You see this object is going this fast at me, and I know that for certain, but what I don't know for certain is the position of that object relative to me. And so the mathematics gets much more complicated because you're trying to infer this over and over at a long distance. So you kind of trade one thing for another, really.
It's also very interesting that, a lot of human visual system is also, it has this quality that, the things that you can focus on and get very high resolution, like it's literally a thumb, if you put your thumb right in front of your eye, the size of your thumb, that's the location you can focus on. Everything is kind of out of focus. And if you look outside, it's actually grayscale. Outside your main vision, the peripheral vision, we lose sense of color in our peripheral vision. So it's basically visual systems are very, very, you need to be, they're demanding, right? And not everything, once you're looking at something, you cannot look at other things, right? So that's why you need such a variety of sensors here. What about ultrasound? Where is that used? What is that used for?
Yeah, what about ultrasound? So basically ultrasound will work the same way, but it's so, the way I understand ultrasound is that it works close distances because it doesn't go very far. There's just a lot more interference for ultrasound. So, in an autonomous vehicle context, what you'll use it for is making sure the vehicle isn't right next to you, right? This is also the sensor you see in Lego Mindstorms. I think, it only has so much distance, but what the readings it does give you are accurate. Yeah.
Okay.
Yeah, but so we've gone, we've done this full sweep, but now once we get to radar and we've gone through all these compensation mechanisms, we realize that radar itself still needs to be compensated for, right? It has much lower accuracy than LiDAR, which is what we preferably would have wanted to use to get that high fidelity. And it's prone to false positives. So even if you see something in distance and you see it has a specific heading in a certain time and you think you're certain about it, it could just be a manhole cover, right? This is an actual case where reflectance, as we said before, interferes with the radar signals and you can get something noisy and unhelpful. So what do we do to compensate for that? The answer, in some cases, is grayscale and color. Going full circle. Because grayscale and color, even though we've gone through all the compensation mechanisms, they still have no range requirement. And you see exactly as a human does, which is way outside the range of radar. So you're fully compensating for these spectrum differences. For instance, Skarsky Robotics had this, I think semi-famous article about how they would not use LiDAR for their systems. And that's because they used radar and telescopic cameras to double check one another through the system. And it worked pretty well. I mean, well, Starsky is out of business as far as I know, but it worked well enough to get them this truck. And it was just a fascinating solution to this whole compensation problem, I think.
Yeah, even Tesla, Elon Musk keeps saying that cameras are enough you can have a completely camera-based autonomous vehicle solution, which I have doubts about, but that's his
Yeah.
opinion.
Yeah, I mean, there are a couple of companies. Mobileye, I think.
Yeah.
Intel also has a fully camera-based autonomous solution. So it's a popular notion, and for, I guess, the basic reason that as a human, you can drive pretty well, and so just adding more information to that human in the loop gets you far.
That's great. So we have already gone 6 minutes over our
I'm sorry.
time. That's okay.
All
That's
good.
okay. This was very interesting. Now, should we open up? Are we done with the slides? Was this the last slide, or we have a few more? We have a few.
Yeah, I just had one more.
Yes.
Basically, check out our site. We're going into open beta soon-ish, and we'd love for you to be there.
Actually, Brandon, can you take 1 minute to tell us more about your company? Because readers would love to know what Tangram Vision does.
Sure. Yeah. So, like I said before, DevOps for perception, but that encompasses a lot. So, whether you're using one sensor or many, you've probably had to go through the trouble of calibration, syncing, data piping, all before you even get to your application, which is you really want to work on, right? So we do all that for you. We're sensor agnostic to the point we can be. We provide calibration and synchronization, streaming for all of these sensors, and we support you from development to deployment and beyond. We're very heavy duty. Like we come from the robotics background. We know what's needed in these robotic settings. So we're set for you in both hobbyist and commercial applications. And like I said, we're going into alphas right now, closed alphas, but we'll soon be in open betas, and we would love for the OpenCV community to try us out at tangramvision.com. So.
That's great. Okay, so we are ready to take questions.
Yeah. Thanks a lot, Brandon. That was a great prezo.
Sorry for going over time.
No, it's all good. I learned a lot. I mean, even though we worked together on some of these things, I actually learned something, which is cool. Starting off with, so Michael here has a question about like a smart catalog of sensors. This is something that I thought was really interesting. Are you aware of any smart catalog of sensors? And if not, do you think this is something that would be really valuable to the community at large? Because I'm not aware of anything like this.
I'm not aware of anything like that either. So smart catalog being sensors that work well together. Sensors.
Yeah. What do you think would be useful there? Like what data to you as an integrator and a developer would be smart to put in there, I guess?
Yeah, I don't know. So it really is all about the application. A lot of roboticists say their applications they don't say this, but it comes across as like, my robot's a special snowflake. 100%, that's not always true. Yeah. But what is always true is that the application is different. That is absolutely unique. And so I wish I could provide a set of sensors that work well together, but at the end of the day, it's about what you're doing, which is why my company is sensor agnostic, right? We don't want to make that choice for you, and we don't expect to ever do so. So sorry, that was a half answer. Very unsatisfying.
No, that's good. Yeah. Thanks. Could you talk a little bit more about the differences between time of flight sensors and say the structure sensor style?
Yeah, so time of flight sets out a pulse, or like a beam, basically, shoots it out, and then registers when it gets back. It's just a beam, it's a pulse. And that's how it calculates the depth through the difference in that beam. But what a more active sensor, a pattern sensor, does is shoots out an IR pattern that is very specific in all areas of that pattern. So if your camera picks up this certain block, it understands that block should be at this depth according to the pattern, but it's actually here. So the distortion of that pattern actually allows you to understand the depth that's coming out. So it's slightly different modalities.
Cool. We've got another question here about vision systems, which is good. Are you aware of any systems or specific sensors that are good for, say, autonomous underwater navigation?
Oh, this is fascinating to me. Autonomous underwater navigation, other than like being IP77 or whatever you could do, the hardest thing about underwater is just the calibration aspect, I think, which sucks to say. But light works differently in underwater, and you need to understand that. So I don't have a suggestion there, but that is something I would love to look into. And also, there are actual autonomous submarine teams that you could talk to on the university level. I know CU Boulder has one. I'm sure they have some specific ideas about what they've used. So.
I wouldn't be surprised if they use sound-based tricks a lot more underwater, because vision is limited, but sound does very well underwater.
Yeah.
And the other thing was, there are a lot of dehazing algorithms, etc., that people use. This was for, at UCSD, there was a whole team who was working on coral reefs, detecting, classifying, etc. But before that, they had to take great pictures of this. So a lot of effort was also spent in making the picture cleaner using, various computer vision techniques. So. Oh,
that's super cool. Interesting.
Got a question here about hyperspectral sensors, which is just fun to say and read. Do you know much about those? This is a new term for me.
Yeah, so it's new for me as well. This is something I've only interacted with through customer conversations. But basically, instead of getting one filter or two filters, you have multiple filters. Sometimes I think I've read one camera that had 40 different spectrum filters. And what you do is basically aggregate them all into this layered image. So for instance, a Bayer color image would have an R, a G, and a B layer. But in a hyperspectral, you would have UV1, UV2, UV3, visible, 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 IR, IR, IR. And that's your whole image. So you get a lot more information out of it, but obviously the data throughput is insane, and you have to be able to handle that.
Yeah, and it has a lot of applications, like when you're doing very high quality color calibration, etc. Like for example, X-Rite, let's say X-Rite, which makes color charts. If they want to make sure that the pigments they are putting on their color charts are accurate every time, they are not just going to look at the colors that are observed through a camera. And the reason is that each camera could have a slightly different filter, right? So they have to make sure that when they say that this is a specific pattern, right, this is a specific color, it is a specific histogram over the visible spectrum, right? For that, they would use hyperspectral imaging to make sure that, this thing is actually reflecting light correctly in the entire visible spectrum, right? So they need many more channels compared to just 3 channels. And the same thing holds with other, when you're trying to find diseases and things like that, when you have these more channels, you can get a higher granularity of information and do more with it.
Absolutely. I think we got time for one more. This one is actually for me. Brandon, you get to play with a lot of different sensors. What is the most fun sensor you've messed with recently?
Oh,
can you say top 3, man?
Top 3.
Done.
I come from a background of depth sensors. So, structure core, Intel RealSense. Like I said, the LiDAR puck from Intel, even though it's new and the software is getting there, the depth is beautiful. And I could see myself using this a lot for hobbyist applications. So, the difficult part about that question is that I too am restricted by the price of sensors I can buy. So there are a lot of cool sensors out there, I think, that we've discussed that I would love to get my hands on. But financially, I'm not there yet. So I'll let you know. Keep you updated.
Appreciate it.
Yeah.
I think we want to move on to our goodies, Satya.
Yeah, so goodies. Let's say, in this section, we ask a question and the first correct answer receives some goodie from us. And today we are going to give away one free course, Computer Vision 1, to whoever answers this question correctly, right? So, and the question is based on, some of the things that we have already discussed. So if you're using a LiDAR sensor, one specific thing, one kind of, let's say weather condition or something, affects the quality of LiDAR information that you receive back significantly. What is that? So I'm not looking at the answers yet. Okay, so the answer is, fog, rain, all of those are right answer, water droplets.
The first one I saw here and just took a screenshot of, looks like Mario is our winner.
Yeah.
Congratulations, Mario.
All right, so congratulations. And, you will receive a free Computer Vision 1 course, and Phil will reach out to you with all the information. And in addition, anybody who's watching this webinar, you can get a 30% discount on our courses, any course, any bundle, by using the coupon code RELU30. So we have activated that coupon code again, RELU30. And if you have any problems, just shoot us an email and we will make sure that you get the discount.
RELU30.
Yes, for a 30% discount. So, so somebody is asking who won the quiz. Can you repeat the name again, Phil?
Yes, Mario Bergeron.
Okay, that's great. Again, thank you so much for attending this. And Brandon, thank you so much for, educating us. It was, we learned so much from you.
Thank you for having me, of course.
Yeah, thanks.
Thanks for joining us, everybody.